Modern enterprise hardware, like ultra-dense NVMe SSDs and DDR5 memory modules, relies on billions of microscopic connections. But as we zoom past the surface mount components and down into the structural reality of a single solder joint, the clean geometry of our digital blueprints meets the messy constraints of physics. The silicon journey begins here, inside the processing equipment of a semiconductor fabrication plant. Engineers use advanced electronic design automation tools to map out flawless logic layouts. But translating those blueprints onto physical silicon requires multi-patterning lithography. Pushing light through lenses to carve nanoscale features inherently introduces microscopic physical variances. Because of these variances, a 300mm wafer never produces identical, perfect clones. Instead, it yields a spectrum of integrated circuits, ranging from the structurally robust to the statistically weak. Since physical defects are a mathematical certainty at the nanometer scale, hardware design must assume a high-risk baseline that every untested chip harbors latent points of failure. This graph plots the electronic reliability model, failure rate against time. The first phase spikes in early failures, the infant mortality zone, where manufacturing variances cause immediate breakdowns. Once weak components fail, the rate stabilizes into a flat section of constant low failure during normal operation. In sectors like aerospace, medical, and high-end industrial, these early life failures cannot be tolerated in the field. A server or a flight controller must arrive already operating in that stable, flat zone of the curve. Hardware engineers don't wait for these failures to happen in the wild. They build rigorous testing gauntlets to artificially compress and accelerate the infant mortality phase within the factory walls. These vulnerabilities are baked into the material itself. In the Czochralski method, a seed crystal is slowly pulled from molten silicon, growing a single ingot. The pulling rate and temperature profile during this growth define the baseline atomic structure of every chip cut from that ingot. Once the wafer is cut, that silicon is etched with memory architecture, which typically falls into two categories, SRAM and DRAM. This is a 6-transistor, or 6T SRAM cell. It uses a complex feedback loop of transistors to hold a bit of data. While fast, this complexity creates more potential points where a microscopic lithography error can compromise a logic gate. On the right is a DRAM cell, which uses just one transistor and one capacitor. But this density requires the capacitor to be constantly refreshed, as the electrical charge naturally leaks out over time. Heat specifically tightens this architectural weakness. High temperatures accelerate charge leakage, and if the capacitor drains faster than the system can refresh it, the data is corrupted. Quality varies across a single wafer. Some DRAM capacitors will leak significantly faster than others, even when exposed to identical operating conditions. These fundamental architectural trade-offs dictate exactly which physical vulnerabilities engineers must stress during the validation process. To weed out these early failures, manufacturers use test during burn-in, or TDBI. Static burn-in is the baseline. The component is subjected to constant heat and elevated voltage, but it sits idle. The goal is to use thermal stress to reveal physical defects like weak solder joints or faulty capacitors. While cost-effective, static testing is limited. It misses the complex logic and timing errors that only appear when a microprocessor is actually switching between states. Dynamic burn-in is much more aggressive. It forces the IC to process high-speed, real-world data patterns while under stress, ensuring the logic gates function correctly even as the physical material expands and contracts. This involves intense thermal cycling, swinging temperatures from -40 degrees to 95 degrees Celsius to push the silicon to its absolute operational limits. This creates a secondary engineering hurdle, protecting the equipment. To prevent these temperature swings from destroying the test motherboards, engineers use miniature chambers that isolate the thermal stress strictly to the module being tested. Dynamic burn-in is significantly more expensive, but it is the only way to verify that complex silicon can survive real-world operational loads without failing prematurely. But the chip itself is only half the story. The printed circuit board that mounts it must also be structurally and electrically sound. Validation starts with automated optical inspection, or AOI. High-speed cameras scan the board for surface-level defects, like missing components, misaligned pins, or bridges of excess solder between connections. However, AOI cannot see underneath modern components, like ball grid arrays, where the connections are tucked directly beneath the chip. To inspect these hidden connections, we use automated X-ray inspection. By scanning through the package, AXI reveals the internal grid of spherical solder joints. X-rays are absorbed by the lead in the solder. A solid, healthy joint looks opaque, but a trapped air bubble or a microscopic fracture allows the X-rays to pass through, creating a dark, hollow void that optical cameras would never detect. Once the physical structure is confirmed, the board moves to in-circuit testing, or ICT. ICT uses a mechanical bed of nails fixture to make direct contact with test points on the board, measuring precise voltage drops to identify shorts or failing components that passed visual inspection. AOI checks the surface. X-ray inspection confirms the internal structure. In-circuit testing proves the electrical pathways, forming a multi-layered validation stack that isolates physical, structural, and electrical failures. After surviving the validation gauntlet, the hardware must be sealed against the actual environments it will inhabit, including humidity, chemicals, and industrial gases. This protection is achieved through conformal coating. Using chemical vapor deposition, a compound called parylene is applied in a vacuum. It conforms to every irregular shape on the board, wrapping components in a seamless, transparent skin. This is vital for hardware and petrochemical plants or mines, where high concentrations of sulfur particles saturate the air. Sulfur can diffuse into resistors and react with the silver conductive material to form silver sulfide. This chemical reaction transforms the conductor into a non-conductor, creating an open circuit that kills the module. By utilizing anti-sulfur resistors and pinhole-free parylene films, manufacturers neutralize this chemical threat before it can compromise the board. This environmental hardening is the final seal, preserving the reliability established during the burn-in phase. A surviving chip is a product of intense selection. It has passed EDA verification, survived the Czochralski growth process, endured extreme thermal stress, and passed a structural X-ray scan. This chart shows the ultimate goal of that gauntlet. By forcing early failures to happen inside the lab, defective chips are identified and removed before they ever reach a customer. Those early life failures that would have happened in a server rack or a hospital are instead triggered and discarded on the factory floor. The result is a failure rate that is effectively erased from the field statistics, leaving behind a stable, flat line of reliability. Modern hardware isn't just defined by its transistor density or the speed of its logic. The true measure of engineering is found in the systems we build to aggressively break our designs before they ever leave the factory.